day, everyone. So that's my pleasure to present you today a lecture about IP-based communication and impacts on power system communications. The learning outcomes of this very specific video will be about the fact that the student will be able to explain IP-based communication in general and justify the IP-based communication specificities for power systems. So, I'm Raphaël Kerr, I'm from École nationale supérieure de l'énergie, de l'eau et de l'environnement, which is part of the University Institut Polytechnique de Grenoble, which is part of University Grenoble app in France. The content of the lecture will be the following. At first, we'll make the link between OSI layers and IEC 61850. At second level, we'll try to focus on layer 2, that is about MAC level and everything related to sample values and GOOS communication in the substation. In the third section, we will focus on the layer 3, which means that I have a IP routing that help me, for instance, to route MMS protocol or any kind of UDP or TCP IP communication in the substation, but as well outside of the substation. So I'm able to reach an external network, and I will finalize with a conclusion. So let's start with the OSI model. So this is really a conceptual model, but I would like to use it to really explain power system communications and at least everything that is related to substation communications. So before jumping into the OSI layers, maybe it's interesting to focus on our object that is a substation. And inside this substation, there is some communications. And communication is ranging between several levels. So at first, you have the substation level. This substation level is of interest because you can find here substation controller and an associated HMI, human machine interface, so to control the different devices. The same remotely substation controller is connected to the SCADA that is kilometers away. Then there is existing different protocols to access to different IDs. So even protection IDs, control IDs, meter IDs, or even protection IDs are all able to communicate with the substation controller with some specific protocols. Below, they have access to the equipment level, for instance, circuit breaker or switches or even current transformer or voltage transformer, and usually all those communication are really proprietary. The final aim of 61850 is really being able to harmonize everything and make sure that there is a single protocol of interest, both at what we call station bus, so between the substation controller and the different IDs, but as well at the process bus level, which is between the different IDs and the components, for instance, circuit breaker, switch, or even primary sensors. So the vision of 61850 is to go from a wired substation with thousands of kilometers of cables for on-off signals or even analogic signals, jumping into fiber optic that will save some space, of course, but that will save some station cabling, building size, commissioning time, maintenance complexity, system drawings, and reduce secondary project costs. 61850 is having a mapping profile that is a little bit special, let's say. So for instance, you have at level 2, we will discover later, some communication, usually for the process bus, for instance, GOOS or sample values, that are using a very low level description of the ICT network. Then you have time synchronization for classical function of control, that is SMTP. Of course, for lower level control, you can have PTP synchronization, usually for sample values and goes. But it is existing some higher level protocols using higher level IP stack, let's say. And so that's why I'm willing to present you what it is about, all this IP description. And let's start with these OSI layers. And being clear, one of my good friends from ICT domain was telling me that OSI layers are as baby layers. In fact, it's very good to explain to the rookies. So it's really baby nappies or diapers. But in fact, no one never implements IP communication in using all the different layers of this conceptual representation. It is related to media layers and host layer, so coming from physical to slowly by slowly application and what you are really using at the computer level. We will focus today only on level 2, so data link, and on level 3, that is network and packets. And let's start with the layer 2 for the communications between two nodes. The level 2 is called the data link layer. It is really providing node-to-node transfer data. And in fact, it's a way to directly connect two nodes to equipments that are willing to discuss together. And in fact, the IEEE 802 is dividing the data link layer into two sublayers. And I will focus on the very first, that is the medium access control, or MAC. And a MAC is really responsible of controlling all the devices in a network, gain access to a medium, and get permission to transmit data. So the MAC address is in fact a unique identifier assigned to a network interface controller, NIC, NIC, for use as network address. And it is really the way to discuss within a network segment. It is good for Ethernet based, Wi-Fi based, or even Bluetooth based. And this MAC address is usually assigned by device manufacturer from the network interface controller and are very often related to a burn-in address. But being clear, it exists some controllers that are able to change their MAC address. Usually, it is a set of numbers in hexadecimal format that are doing this unique address of this network interface controller. Using layer 2 is usually related to the maximum size of the communication you can have between two nodes. And they have been defined, at least for the Ethernet, with a maximum size of 1,500 bytes, which is quite low and which is limiting all level 2 communications to this very specific value. So that means that for a simple value or sample measured value, in fact, there are some communication existing at level 2, describing between one MAC address to another some data. So for instance, let's say you have a merging unit getting data from a sensor, and that is sending on the process bus some values that are periodic and that are giving the time-stamped value of a current or a voltage. Being clear, it's not really a timestamp, but it's a counter from 1 to 4,800 related to the last standard that will give sampling with, then you can understand, a frequency sampling of 4,800 Hertz. It is existing a second communication very specific to power system, which is called GOOS, Generic Oriented Signal for Substations. that is again at level 2. And this level 2 is again from or between two different network interface, and that are sending some informations related to what you want to transmit. Typically, at a goose level, we'll transmit a trip order to a ID controller that is controlling a breaker, and that will allow to trip a short circuit current, for instance. If we consider elevating of one layer, then we jump to the layer 3, which is a multi-mode network, including both addressing, routing, and traffic control. So the network layer is a way to provide functional and procedural means to transfer packets of information from one node to another node that can be connected to different networks. And compared to the level 2, if the message is too large, it will be splitted into several messages or several fragments of messages. So one node, the emitter, will send the data in different fragments, and the fragments will be reassembled by the recipient, the other node. And being clear, it doesn't mean that you have a network layer that is always guaranteeing you the fact that you will receive all the data. So in fact, UDP protocol will send the data without acknowledgement of receipt, versus TCP, that is a network layer protocol that is providing reliable message delivery. So, in order to configure a network interface able to communicate at level 3, some parameters must be set up. At first, IP address, and then the subnet mask, and if necessary, the gateway and the DNS. So let's start with the IP address. IP address is the host identification number for proper communication between devices, and more than that, as you learned just before, between networks that can be separated. It is used to identify network components, and I will describe only the IPv4 implementation, which is a 32-byte number of very specific. But in fact, it's a little bit not uneasy to read 32-byte number. So usually we split it as 4 separated bytes called octet. It's 8 bits in binary forms. And those 8 bytes give 256 combinations. So each octet represents a number from 0 to 255. It's much more easy to read rather than the 32-byte number. So if we take as example the Erasmus website, so when you type essence-erasmus.org, in fact the IP address is 92, 53, 112, 193, which is in binary a very long number. And if you put all the number together and you put it in decimal, it will give a shorter number. But this shorter number, of course, is just uneasy to remember, and the IP address is much more easy to read with the separation of 4 octets. And keep in mind that usually in a substation, addresses are private, so they should not be seen from the internet. And another point, if you jump into IPv6, instead of 32-byte number, you jump into a 128-byte number. But it's exactly the same idea. The second level is the subset mask. So this is a mask that is used to distinguish the subnet part of the IP address, as well as the part that is the host address of the specific subnet. Subnet is a very specific network on which you will connect all the different components. You want them being able to communicate together without having to rely on a gateway I will describe later. For IPv4, it is a form of 4 8-byte numbers, again octets, in decimal format and separated by periods. For instance, 255, 255, 255, and 0. So the mask value has to be known to all the different routers and computers in this given subnet. So when you are comparing the address mask specific with a specific IP address, so for instance 192.168.1.122, the router is notified which part of the address identifies this subnet, in this very specific case 192.168.1, and which refers to the device within the IP address assigned. So this is really the address ending. So let's use another example. You have the IP address of 192.168.10.111 with again a subnet mask that is allowing to have below 256 address. Then you know that the network address is 192.168.10.0. We need to use a gateway whenever we need to jump from, let's say, one network to another. And thus, the gateway is a network device that will act as an entry point from one network to another. So the host sends all the packets directly to other hosts outside the local network to the default gateway. And usually we know the IP address of this specific gateway. This is exactly what we are defining on the different network interface. Let's be clear, with the evolution of the network, the concept of gateway has become really virtually parallel with the role of a router. So the gateway is created at the network border to manage communication of all data exchanged between the internal network, defined by the mask, and the external ones. The next level is the DNS, and it's in fact a way to exchange a, let's say, numeric format into a domain format, much easy to read. So DNS means domain name system, and this is a service that is used to resolve IP address related to a domain name. The translation of numeric to domain is performed by an appropriate DNS server. And so whenever you're receiving a response with the numeric address, it's easy to say, okay, I want to communicate with this specific IP address and to find it over the world. So again, when you are typing essence-erasmus.org, a DNS server that you did define will give you the number of the IP address we already discussed, 92, 53, 112, 193. Now let's jump to the very last part of my presentation of today. So as a conclusion, I want to highlight the fact that you need at substation level or even at smart grid level efficient communication infrastructures. And the communication in a primary substation is related to a very high reliability communication network. Indeed, if you want to have protection devices relying on a communication network, then you cannot stop them for 1% of the time. And with the IEC 61850, that is including both field and process bus, the underlying concept is still based on Ethernet basics. That's why I was presenting them in this very short video. And so power system engineers must master some basics about communication and be ready to exchange with communication experts to build resilient and robust smart energy systems. If we remind the proposed learning outcomes from the beginning, I was hoping that at the end of the lecture, the student should be able to explain AP-based communication in general and justify the IP-based communication specificities for power system. You have a reference list with different links. I advise you to go where you will find some more detailed information than I was giving to you today. So thank you for your attention and good luck for the next part of the summer school.